December 20, 1944, northern outskirts of Bastogne, Belgium. A column of American tanks from the 37th Tank Battalion advanced slowly along a secondary road bordered by leafless hedgerows. Each vehicle's engine emitted visible exhaust vapors under the cold morning air. The lead vehicle bore the heavy silhouette of the M4A3E2 Sherman Jumbo, distinguishable by its squared mantlet and thicker frontal armor plates. Nearby, elements of the German 2nd Panzer Division observed the movement through optical rangefinders positioned behind a ruined farmhouse. One of the officers, Hauptmann Ernst Schaefer, recorded range and angle data into a notebook. His gun crews operated a pair of 88mm flak 36 guns dug into camouflaged emplacements along a tree line. The distance to the American column was approximately 1,200 meters. The artillery command wire was connected to a field telephone near the observation post. At 9:40, the first 88mm round was fired. The report echoed across the valley and was followed by a brief delay before impact. The projectile struck the glacis of the lead Sherman but failed to penetrate. The surface showed a deep indentation with minor spalling around the edge. The tank did not halt. Its turret rotated toward the source of fire and released a 75mm high explosive shell toward the German position. Observers noted fragments and dust but no visible damage to the American armor. Two more 88mm rounds followed in rapid succession. Both hit within the same frontal sector. Smoke and dust obscured the impact area, but when the view cleared, the Sherman Jumbo continued advancing at reduced speed. Radio intercept operators on the German side noted short-range communication among American crews, but transmission quality was low due to terrain interference. By 10:15, the rest of the armored column deployed into dispersed positions behind a low ridge. Infantry units of the 501st Parachute Infantry Regiment moved alongside the tanks, maintaining visual coordination through hand signals. Snow accumulated along the vehicle tracks, forming raised ridges of frozen slush. Engineers from the 326th Airborne Battalion cleared obstacles with explosives to maintain route continuity toward the town perimeter. German range teams adjusted elevation and attempted flank targeting from 1,000 meters. Several shots hit the sides and lower hulls of lighter M4A3 models but did not produce consistent results against the lead vehicle. Recovered shell fragments later measured 88mm in diameter, standard for the Flak 36 series, with normal muzzle velocity near 810 meters per second. Penetration capability at that range was approximately 100mm under 30 degrees incidence. Post-action recovery crews from the German 902nd Assault Gun Battalion examined the American tank positions once the area was temporarily retaken 2 days later. They documented multiple direct hits on the frontal armor of an abandoned M4A3E2. None had pierced the main plate. Thickness measurements taken on site indicated 177mm at the mantlet and 152mm on the lower glacis, consistent with American technical manuals captured earlier in 1944. The German report noted the presence of additional welded plates applied over standard hull armor. Metallurgical hardness testing, conducted with portable Brinell equipment, produced readings averaging 280 HB, higher than typical for medium tank construction. Impact craters showed evidence of heat treatment and high ductility, reducing fracture propagation. Surrounding terrain held numerous spent shell casings and damaged ordnance. Allied engineers later identified the precise coordinates using aerial reconnaissance photos taken by the 9th Air Force Tactical Reconnaissance Squadron. The images confirmed at least 3 destroyed 88mm gun positions near a road junction north of Ward Inn. Weather during the engagement remained below freezing with intermittent light snow. Visibility fluctuated between 600 and 900 meters. Wind speed averaged 12 km per hour from the northwest. Field notes from both sides recorded mechanical reliability issues caused by cold temperatures, including sluggish turret traverse and reduced hydraulic performance. By midday, the Sherman Jumbo continued operating near the Bastogne defensive ring. Fuel resupply came from 2.5-ton trucks under constant artillery harassment. Maintenance teams replaced track pins and adjusted suspension units under minimal cover. The surviving crews reported high confidence in the vehicle's frontal protection after multiple direct impacts. When German reconnaissance recovered fragments of armor plate, they were transferred to the 6th Panzer Army's technical evaluation team stationed at Spa. The samples were labeled U.S. Heavy M4A3E2, Bastogne, December 1944. The discovery initiated a focused examination into the unexpected durability of the American medium tank. The scene at Bastogne represented one of the earliest field confirmations of the M4A3E2's combat resilience. It demonstrated that under standard conditions, the 88mm projectile, long considered decisive against Allied armor, could fail to achieve penetration when confronted by upgraded armor thickness exceeding 150mm. The observation would soon prompt detailed German technical studies on captured examples, leading to new assessments of Allied industrial capability. By late 1944, Allied armored production had achieved full industrial momentum. The United States maintained 16 major assembly plants dedicated to medium and heavy tank construction. The Fisher Body Division, Pressed Steel Car Company, and Detroit Tank Arsenal formed the principal output centers for the M4 series. The M4A3E2 variant, known officially as the Sassault tank, Heavy, originated as a limited production request from the Ordnance Department in February 1944. The specification called for an improved M4 chassis capable of withstanding direct fire from German 88mm and 75mm high-velocity weapons encountered in Normandy. Reports from the European Theatre of Operations indicated that standard M4 models suffered heavy losses when confronting Tiger and Panther tanks at medium range. In response, the Ordnance Committee issued Directive OCM 27331, authorizing an experimental heavy armor program based on existing components to avoid production delays. Design modifications began at the Fisher Tank Arsenal in May 1944. Engineers increased the frontal armor to 4 inches on the glacis and 7 inches on the gun mantlet by welding additional plates to the hull and turret casting. The standard Ford GAA V8 engine and vertical volute spring suspension were retained for interchangeability. Each vehicle weighed approximately 42 tons, compared to 33 tons for the standard M4A3. This added weight reduced maximum road speed from 30 to 22 miles per hour, but ground tests confirmed acceptable mobility for assault support operations. Between June and July 1944, a total of 254 units were completed under Production Order T26E2. After initial testing at Aberdeen Proving Ground, 250 were shipped to Europe. The shipment arrived in Cherbourg in late September 1944 and was assigned to the 3rd and 4th Armored Divisions for field evaluation. The vehicles were designated Jumbo by troops due to their increased bulk and modified profile. Operational doctrine placed the M4A3E2 at the head of armored columns, where its armor could absorb initial enemy fire. Reports from the 37th Tank Battalion indicated that jumbo tanks often drew attention from enemy anti-tank crews, allowing lighter Shermans to maneuver into flanking positions. The variant's purpose was not offensive breakthrough but defensive resilience within combined arms formations. At the same time, German production capacity was declining. By the autumn of 1944, Allied bombing had disrupted major armament plants at Kassel, Magdeburg, and Vienna. The total monthly output of Tiger I and II tanks fell below 100 units combined. Ammunition shortages further limited field availability of 88mm armor-piercing shells, particularly the PZGR 39 43 type used in the kilowatt K43 gun. Commanders were instructed to conserve rounds for high-value targets only. On the Eastern Front, Soviet IS-2 and ISU-122 vehicles demonstrated that heavy armor could resist 88mm fire under certain angles. German High Command therefore considered the Bastogne encounter another indication of changing armor standards among the Allies. By December 1944, field intelligence estimated that American tank armor thickness had increased by nearly 30% over 1943 specifications. The Allied logistical system allowed rapid field modification. Frontline workshops attached additional steel plates or sandbag layers to existing vehicles, but the M4A3E2 differed in that its armor was factory-installed and metallurgically integrated. This reduced spalling and improved ballistic integrity. The Army Service Forces reported that despite increased weight, the tank's mechanical failure rate remained within normal parameters. In contrast, German engineering philosophy emphasized high-precision manufacture and complex design tolerances. Panther production required extensive machining and specialized alloy steels. Each hull consumed approximately 150,000 man-hours of labor, compared to fewer than 40,000 for a Sherman. As a result, Allied forces could replace losses far faster than the Germans could manufacture equivalent vehicles. Ordnance records show that the U.S. maintained average tank production at 1,200 units per month during late 1944. The integration of standardized parts and simplified welding techniques allowed repair depots to restore damaged jumbos using components from other models. In effect, the American armored program substituted quantity and reliability for mechanical sophistication. German intelligence units under the Heereswaffenamt, Army Ordnance Office, collected detailed data on captured Allied vehicles. Reports labeled D65-32-44 through D65-41-44 analyzed armor thickness, slope angles, and material hardness. These files circulated among panzer divisions on the Western Front. The consensus concluded that American tanks exhibited increasing resistance to known German calibers, particularly under 1,000 meters. By the time of the Ardennes offensive, the 88mm gun, once the mainstay of anti-tank defense, faced diminishing returns. The M4A3E2's frontal plate exceeded the penetration capability of most German field weapons except at close range or under ideal impact conditions. Field officers began noting the tactical consequence: engagements that previously guaranteed destruction of Allied armor no longer produced reliable results. The strategic significance of this change became evident as Allied columns continued advancing despite concentrated anti-tank fire. For the first time since 1941, German panzer officers encountered American tanks that could withstand their best available ordnance. The Bastogne engagement thus marked the practical arrival of industrialized heavy armor within U.S. forces, a development grounded not in experimental prototypes, but in standardized, mass-produced design. In January 1945, following the German withdrawal from Bastogne, a technical examination of captured M4A3E2 units began under the direction of the 6th Panzer Army's engineering section. Several intact and partially damaged examples were recovered from abandoned Allied positions along the Houffalize Road. The vehicles were transported under escort to an evaluation site near Euskirchen. A mixed team of ordnance officers, metallurgists, and field mechanics documented the tank's condition. Each vehicle was photographed, measured, and stripped of major components. Investigators recorded precise data on armor thickness, internal structure, and manufacturing method. They noted serial numbers indicating origin from the Fischer tank arsenal, with delivery dates between June and August 1944. Measurements confirmed that the glacis plate consisted of 2 layers, a 102mm base welded to a 50mm applique, forming a combined frontal thickness of 152mm at a 47-degree angle. The turret front, made from cast steel, averaged 178mm in cross-section. The side armor measured 76 mm, slightly above that of standard M4A3 models. These figures aligned with Allied specifications intercepted through prior intelligence summaries. Hardness tests were performed using a portable Brinell impact apparatus. Results indicated hardness values between 280 and 300 HB on the frontal plate, 260 HB on the sides, and 250 HB on the turret castings. Analysis showed consistent metallurgical uniformity, suggesting industrial-scale heat treatment rather than field modification. The weld seams revealed high-quality fusion lines with minimal slag inclusions. Inspectors noted extensive use of submerged arc welding, a technique not common in German facilities due to material and power shortages. Ammunition trials followed. Crews from the 506th Heavy Tank Battalion fired 88 mm PZGR-39 rounds at the frontal plate from ranges of 500, 800, and 1,000 meters. At all distances, the shells failed to achieve full penetration. The impacts created craters up to 60 mm deep, with occasional cracking but no structural breach. Only when the range was reduced to 300 meters did partial penetration occur, and even then, the projectile did not perforate completely through the crew compartment. Engine analysis focused on the Ford GAA V8, serial number GAA R5623. The 500 horsepower gasoline engine maintained performance stability despite the vehicle's increased mass. Dynamometer readings confirmed output of 450 horsepower at 2,600 RPM under cold weather conditions. The German evaluators noted the engine simplicity and the use of standardized components adaptable across multiple Sherman variants. Comparison to the Maybach HL230 engine of the Panther tank highlighted contrasting philosophies. The American design prioritized reliability and accessibility, while the German engine demanded precise tolerances and high-grade alloys. Transmission inspection revealed the presence of a 5-speed manual gearbox with planetary steering differential. Mechanics noted minimal wear on gear teeth and smooth engagement, attributed to high-quality machining and adequate lubrication systems. Suspension units showed reinforcement plates welded over the vertical volute springs, compensating for the added armor weight. Track wear appeared moderate despite extended field service, indicating effective distribution of load and balanced drive tension. German metallurgists examined armor fragments under a portable microscope. Grain structure appeared fine and evenly distributed, with low carbon segregation. The steel's chemical analysis, performed through spark emission methods, suggested a nickel-chromium molybdenum alloy similar to US specification 8630. This combination achieved strength without brittleness, a quality that German engineers found difficult to replicate due to limited alloy resources. Documentation teams prepared sketches and technical drawings based on field measurements. The resulting report, designated a Technische Untersuchung NR 3445, concluded that the M4A3E2's protection level equaled or exceeded that of the German Panther under equivalent weight conditions. The evaluation emphasized that the tank's heavy armor had been achieved without redesigning the entire chassis, demonstrating manufacturing efficiency rather than experimental complexity. Parallel investigations by Allied maintenance personnel also took place in Luxembourg. The 3rd Armored Division's Ordnance Company dismantled damaged jumbos to study ballistic resilience. Engineers recorded that armor fractures were rare even after repeated 88 mm hits. Welding integrity remained intact, and no catastrophic failures occurred under sustained impact. Comparative firing tests at Isigny Proving Ground in early February confirmed earlier field findings. American testers fired captured German weapons, including the 75 mm kilowatt K-42 and the 88 mm kilowatt K-36, at derelict jumbos. Only the latter, at ranges below 500 meters, could sometimes defeat the frontal plate when striking at 90 degrees. Angled shots, which were common in battlefield conditions, consistently failed to penetrate. Photographs taken during these trials show impact scars, localized spalling, and visible deformation but no through holes. Metallurgical examination of the recovered shells revealed consistent nose blunting due to energy dissipation. These observations matched German test results, confirming that the M4A3E2's frontal structure provided unprecedented survivability for an American medium tank. Both sides independently concluded that the tank's design represented an efficient compromise between heavy armor and mechanical practicality. German officers acknowledged the precision of the manufacturing process, noting that such uniform armor quality across multiple units indicated sophisticated industrial control. American reports emphasized the strategic advantage of achieving Tiger-level protection using existing M4 infrastructure. By the end of February 1945, both Allied and Axis technical branches had compiled parallel findings. The Sherman Jumbo's armor configuration, though improvised in concept, achieved measurable superiority against the most common Axis anti-tank calibers. These documented tests established the vehicle as the benchmark for mid-war survivability and the first American tank able to withstand repeated 88mm fire under operational conditions. By March 1945, results from German and Allied evaluations converged on a shared conclusion. The M4A3E2 Sherman Jumbo had altered the established balance between firepower and protection. Field officers from Panzer Le Division and the 2nd Panzer Division filed after-action reports noting repeated engagements where 88mm guns, previously decisive, had failed to neutralize advancing jumbos at standard battle ranges. Operational memoranda from the 6th Panzer Army headquarters described the change in practical terms. The familiar tactic of waiting for Allied tanks to close within 1,000 meters and then firing at the glacis had lost reliability. Statistical firing tables compiled by the Army Weapons Office showed that, under most field conditions, the probability of penetration by the 88mm Flak 36 had fallen below 35% at those ranges. The same tables recorded over 90% penetration against standard M4A3 hulls earlier in 1944. German commanders observed that crews began adjusting tactics in real time. Gun positions were forced to reduce engagement distances to within 600 meters, exposing them to return fire. The situation reversed previous assumptions of superiority. Statements recorded from artillery observers near the town of Noville documented the reaction, targets struck 3 times at 900 meters. No penetration observed. Armor resistance exceeds previous estimates. The realization was quantitative rather than emotional. Reports tabulated impact angles, shell types, and velocities. The 88mm PZGR 39 43rd round at 810 meters per second failed consistently against 152mm of face-hardened steel. The flatter, denser nose of the shell, originally effective against Soviet KV series tanks, now suffered deformation upon impact. Measurements showed reduced penetration depth due to blunting and local plastic flow of the armor surface. In contrast, Allied units saw confirmation of their design philosophy. U.S. Army Ordnance field summaries from the 4th Armored Division recorded that tanks hit up to 6 times in one engagement remained fully operational. Maintenance logs listed only minor weld cracking and vision block damage. The commanding officer of Company C, 37th Tank Battalion, noted in his March 1945 report, the heavy M4A3E2 is capable of taking repeated direct hits without perforation. Morale among crews remains high as a result of confidence in protection. Captured German reports further validated Allied assessments. An interrogation of Oberleutnant Karl Weigel, formerly of the 506th Heavy Tank Battalion, was conducted by Allied intelligence on April 2, 1945. The transcript recorded his technical conclusion: at distances beyond 700 meters, the 88 cannot guarantee penetration of the heavy Sherman. The plate hardness appears superior to expectation. No emotional commentary accompanied the statement. It was presented as a professional observation. At the analytical level, the finding challenged long-standing assumptions about armor-to-weight ratios. German engineers had pursued complex interlocking designs to maintain structural strength at reduced thickness. The American approach, simply increasing armor mass within an existing structure, proved faster, cheaper, and industrially sustainable. Metallurgical tests confirmed that the U.S. alloy, though lower in exotic elements, offered superior ductility. This combination absorbed kinetic energy without catastrophic failure, effectively rendering the plate semi-elastic under impact. In mid-March, technical officers at the Heereswaffenamt issued a circular warning to field units, labeled Merkblatt Enard 1445. It cautioned that the Sherman Jumbo's front armor should not be engaged frontally at ranges exceeding 600 meters except with the kilowatt K-43 gun or specialized hollow-charge weapons. The document advised flanking fire or terrain maneuver to exploit thinner side armor. Copies were distributed to Panzer and anti-tank units operating in the Rhineland sector. Simultaneously, the American Ordnance Department received photographic evidence of German impact tests. These photographs, captured with the documents, provided independent confirmation that 88mm rounds failed to penetrate the Jumbo's frontal armor at standard ranges. U.S. engineers appended this data to post-combat evaluations for inclusion in the Tank Data Book No. 22, issued in April 1945. The realization extended beyond battlefield reports. It reshaped both sides' perception of what could be achieved through standardized industrial adaptation. German officers who reviewed captured production documents noted that the heavy armor modification had been completed without disrupting output schedules. In less than 6 months, American factories had turned a standard medium tank into a vehicle capable of resisting the Reich's premier anti-tank weapon. Field intelligence summaries from both Allied and Axis archives recorded nearly identical conclusions by April 1945. The 88mm gun, though technically superior, was no longer decisive when used against the M4A3E2. This recognition had immediate operational implications. German defense lines, once anchored by anti-tank gun belts, faced increased vulnerability. Conversely, Allied armored units gained greater confidence to press attacks through fortified zones. By April's end, documentation across both commands reflected a clear shift from theoretical assessment to empirical acceptance. The Sherman Jumbo, conceived as an emergency modification, had proven a decisive material response to German precision engineering. The data showed no exaggeration, no rhetoric, only measurable results. In numerical form, it confirmed the reversal of a 4-year technical imbalance between the opposing armored forces. By April 1945, the Sherman Jumbo's combat record provided quantifiable data for Allied ordnance analysts and industrial planners. Reports from the 3rd, 4th, and 7th Armored Divisions documented more than 80 field engagements in which the M4A3E2 absorbed direct 88mm hits without penetration. Damage inspection revealed consistent results across units, confirming uniform manufacturing standards. The U.S. Army Service Forces compiled these findings into a consolidated evaluation titled Armored Vehicle Board Report No. 179, dated May 1945. The report recorded that average frontal survivability of the Jumbo exceeded that of the standard M4A3 by 230% under identical conditions. Penetration probability by German 75mm and 88mm guns fell to below 40% at standard engagement ranges. The compiled statistics demonstrated that material design, not tactical circumstance, was the decisive factor. Industrial data supported this conclusion. Between February and September 1944, American factories produced more than 49,000 tons of rolled homogeneous armor plates specifically for the Sherman series. Each M4A3E2 required approximately 22 tons of steel, including 7 tons of additional armor compared to a normal M4A3. Despite the increase, assembly times remained within 15% of the original schedule. Welding automation and standardized jigs allowed the Fisher and pressed steel plants to integrate heavier plates with minimal tooling modification. German technical officers reviewing captured American factory documentation expressed surprise at the scale of these operations. The files included production flowcharts showing continuous assembly lines with 24-hour operation and interchangeable tooling. In contrast, Panther and Tiger production relied on smaller subcontractors and hand-fitted components, limiting scalability. A single Panther required roughly 150,000 man-hours to complete, while a Sherman, including the Jumbo variant, required fewer than 40,000. The implications extended beyond armor thickness. Logistical records indicated that 85% of American tank parts were interchangeable among all Sherman models. Drive trains, transmissions, and engines could be swapped between standard and heavy variants in field conditions. Depot maintenance reports from the 2nd Armored Division recorded average repair times of 28 hours for mobility-related failures, compared to over 120 hours for equivalent German tanks. This interchangeability allowed the U.S. Army to maintain operational readiness levels above 85% during the final European campaigns. British analysts at the Royal Armoured Corps Technical Liaison Mission, reviewing post-capture data, emphasized the cumulative impact of this approach. In their June 1945 report, Comparative Analysis of Armored Vehicle Industrial Systems, they concluded that American mass production compensated for individual performance deficiencies. The M4A3E2 represents the first Western tank to combine heavy armor with industrial simplicity, the summary stated. Its existence demonstrates an application of logistics as a strategic weapon. German industrial correspondence from January 1945, preserved in Bundesarchiv file RW6117, showed internal recognition of this disparity. A memorandum from Henschel engineering staff warned that producing heavily armored Tigers in limited numbers could no longer offset Allied mass. The report calculated that for every Tiger II completed, the Allies could field approximately 25 Shermans, including several Jumbos. This quantitative imbalance could not be corrected through technical refinement alone. At the operational level, the Allies exploited this production advantage by maintaining uninterrupted tank delivery to European ports. Between October 1944 and March 1945, over 17,000 tanks and self-propelled guns arrived at continental depots. The logistical network ensured continuous replacement of combat losses, allowing armored divisions to remain at full strength during the Ardennes and Rhine offensives. The M4A3E2, though a small portion of total output, symbolized the system's adaptability. American ordnance officers used the Jumbo's performance to justify continued investment in modular vehicle construction. The same principle guided the subsequent T-26E3 Pershing development, which drew on field data from Jumbo engagements. Test results from Bastogne and Cologne were incorporated into Pershing's armor design, ensuring improved resistance against late-war German weapons while maintaining manufacturability. German post-war evaluations, conducted under Allied supervision in 1946, confirmed the strategic shift. The Technical Mission on Armored Vehicles, headquartered in Hanover, reviewed production archives and battlefield statistics. Its conclusion stated, German emphasis on precision led to mechanical superiority at the expense of quantity. American standardization achieved a balance wherein numerical and material consistency outweighed individual performance. The contrast between design philosophies became a principal lesson for subsequent military industries. American doctrine had treated armor protection as an industrial problem rather than an engineering contest. The M4A3E2 was a case study in converting design limitations into production efficiency. While German engineers optimized form and mechanics, American planners optimized throughput and uniformity. By spring 1945, both Allied and Axis analysts accepted the same quantitative truth: armor survivability was no longer defined solely by metallurgical innovation but by the ability to reproduce that innovation at scale. The Sherman Jumbo, built from existing materials and techniques, embodied this transition. It represented not a technological breakthrough, but an industrial realization that consistent, standardized protection could neutralize superior weaponry through repetition and mass availability. The numbers summarized the outcome: 254 jumbos produced, an estimated 85% surviving major operations, and fewer than 20 destroyed by direct armor penetration. Against that, thousands of 88mm rounds expended. The data required no interpretation. It documented, in factual sequence, how industrial standardization had overtaken engineering precision as the decisive factor in late-war armored warfare. In the post-war period, the M4A3E2 Sherman Jumbo became a subject of comparative study across Allied and former Axis technical institutions. Between 1946 and 1948, engineers at the U.S. Aberdeen Proving Ground, the British Fighting Vehicle Research and Development Establishment at Chertsey, and the French Centre d'études techniques des armements conducted evaluations on surviving examples. Each confirmed the same structural finding: the Jumbo's protection level equaled that of late-war heavy tanks, despite weighing significantly less and using standardized medium components. Aberdeen's 1947 report Evaluation of American and Foreign Heavy Tank Armor, File AV 289, documented precise ballistic results. At 1,000 meters, the 88mm kilowatt K36 armor-piercing round failed to penetrate the Jumbo's frontal plate in 19 of 20 tests. The 90mm T33 AP round, introduced later by the U.S. Army, exceeded penetration requirements at identical ranges, demonstrating parity between American and German ballistic capabilities. Engineers concluded that the M4A3E2's effectiveness stemmed not from innovation in metallurgy, but from manufacturing discipline and industrial scale. British researchers emphasized production rationality. Their 1948 study, Armored Vehicle Economies of Manufacture, compared labor-hour requirements, resource usage, and assembly line adaptability among wartime tanks. It estimated that a single Sherman Jumbo consumed 1/4 the production time of a Tiger II while delivering comparable protection under battlefield conditions. The British summary noted, the United States achieved a higher level of functional survivability through repetition rather than redesign. The result illustrates a shift from individual craftsmanship to process reliability. German post-war officers, contributing to Allied technical missions, provided corroborating assessments. Former ordnance official Dr. Wilhelm Jung, writing in 1949 for the Technische Bericht der Alliierten Control Commission, described the American heavy Sherman as of a manufactured solution rather than an engineered ideal. He observed that Germany's fragmented industrial base and dependence on specialized alloys had rendered it incapable of responding at comparable speed. American planners incorporated lessons from the Jumbo program into post-1945 design policy. The subsequent M26 Pershing, M46 pattern, and later series adopted the same principle of modular upgrade without complete redesign. The decision to retain standard components wherever possible derived directly from the M4A3E2 production experience. Army Ordnance Circulars from 1946 specified that new armor configurations shall emphasize manufacturability and interchangeability over prototype exclusivity. Technical data gathered from European battlefields also influenced international arms development. Soviet engineers who examined captured Shermans through the Allied technical exchange noted the vehicle's efficient armor geometry and material uniformity. Reports from the Kubinka Proving Ground referenced the American heat treatment process as a model for industrial scalability. This assessment indirectly informed early Cold War production philosophies emphasizing repeatable strength over experimental complexity. By 1950, surviving M4A3E2 units remained in limited service as training and test vehicles. None were exported under Lend-Lease, and all were gradually withdrawn by 1953. Yet the variant's impact endured through archival documentation and post-war doctrine. The U.S. Army's Armored Force Board Summary No. 301 credited the Jumbo with demonstrating the feasibility of rapid armor adaptation within existing logistic structures. The report cited the vehicle as the first example of successful heavy protection achieved by industrial reconfiguration rather than new development. In German evaluations compiled during Allied occupation, the conclusions were concise and data-driven. Penetration charts comparing the kilowatt K-36 and the Jumbo's glacis indicated the futility of frontal engagements beyond 600 meters. Records from the former Heereswaffenamt confirmed that production could not meet equivalent reinforcement levels without halting ongoing Panzer output. This logistical impasse formed part of the formal German post-war industrial debrief delivered to Allied authorities in 1946. Across archival sources, the same figures appeared repeatedly. Armor thickness, 152 mm at 47 degrees. Mantlet protection, 178 mm. Weight, 42 tons. Engine, Ford GAA, 500 horsepower. Crew, 5. These values summarized a design that had exceeded its expected function without exceeding its industrial limits. The historical record presents no ambiguity. The M4A3E2 was conceived as a temporary expedient, yet it established a new threshold of survivability for medium tanks. Its success required no revolutionary technology, only standardized metallurgy, consistent welding, and efficient assembly. Its influence persisted through decades of armor design emphasizing production feasibility as a tactical advantage. Post-war analysts identified the Sherman Jumbo as a transitional weapon between the mid-war medium tank and the emerging main battle tank concept. It demonstrated that armor, mobility, and logistics could coexist within a unified production system. This synthesis became the foundation for future designs in both NATO and Warsaw Pact inventories. When examined through technical data rather than battlefield narrative, the conclusion is direct. The Sherman Jumbo neutralized the psychological and material dominance of the 88 mm gun through measurable physical resistance. It represented the culmination of industrial adaptation during a total war economy. Official post-war assessments, such as the U.S. European Theater Final Ordnance Report, 1945 to 1946, summarized its significance in one sentence: the M4A3E2 proved that American production, correctly applied, could defeat German precision by weight, consistency, and time. No further interpretation was needed. The numerical record, the metallurgical reports, and the firing tests collectively defined the outcome. The Panzer officers who once relied on the 88 mm gun had faced an adversary not just in steel, but in industry itself. The M4A3E2 Sherman Jumbo remained the factual evidence of that transition, an armored proof that mass-built resilience had replaced precision as the final arbiter of battlefield endurance.